Hello guys, in this video we will going to be talking about how a ship floats and the Archimedes principle, which is kind of cool principle to know about, and it's useful to figure out how a ship floats. Now let's think about an object, a ball, and I choose a ball because a ball is pretty, it's mathematically pretty. It's beautiful, it's just easy to deal with. Let's think about a ball that is submerged underwater. Now note that a ship is not necessarily submerged underwater unless it's a submarine, but some part of the ship will always be underwater, so it doesn't really matter, does it? Now, to consider how this ball doesn't just randomly sink in, we have to consider the forces. If you're familiar with Newtonian physics, this should be very obvious for you. Even if you're not, just follow me. So now, what are the forces acting on this ball? Well, first of all, we assume that we are on this planet Earth, so we have gravity facing downwards. Right? This is due to Earth's mass, and the gravity would be mg. This could be familiar. The g is the gravitational acceleration on this planet, which is always a fixed value, 9.81 something something. And then the m is the mass of this sphere. Now, with this in mind, the ball would just keep on accelerating downwards until it falls. But does it? Well, it may or may not, depending on the other forces acting on this, which would be this and that. So this is the pressure downwards, the downwards pressure that is from the air and the water, and this is the upwards pressure from this water over here. So to calculate this downward pressure, we will not consider the whole ball because the ball, it's a lot to consider, and also it's not for general. We will consider a nice bar that happens to look like this and has a very small area A, and so it's like relatively flat, and then it will have a height h. Right, this is the height h, this is the area A, and the volume of this would be A times h. If you are familiar with mathematics, you should probably know about this. So how does these forces by pressure works? Well, we all know that pressure is force over area, and that means that force is P times A. So all the water here and the air here pushing this ball down can be calculated by F equals P times A. And let's say the pressure here is PO, right? And then the pressure here, what would that be? Well, that pressure would be PO plus something. It should be larger because it's deeper underwater, and the value of that actually is rho GH. Now let me explain. The rho, it's not P, it's rho, represents the density of water, right? And this kind of makes sense because, you know, there's this amount of more water, so it will pull down the water by rho GH amount. Yes, there's like, you know, if you think about it, there's like rho GH water here, so it pushes down by that much. You might think it's intuitive, you might not, just remember it. It's a pretty nice formula. And then from here, you can derive that the force here is POA. And the force here is PO plus rho GH A. So now we've got this pretty nice formula that calculates all the forces. And now what would then be the resultant force of this air and pressure? Well, we can calculate this by subtracting one from another. Let's consider a direction downwards. So we will subtract the upwards force from the downwards force. So this is the downwards force minus the upwards force. So H A F net. So then, you can like simplify this. This goes here, this goes away, and what you are left with is rho G H A. Now, what was this? HA, height, times area, would equal to the volume. That's right. And that is why the F net is minus rho G V, the volume. The volume of what? The volume of this random bar we found out about. So then you can think about the sphere as the accumulate of these bars, like a bar bundle. And then you can then find out the formula that the net buoyancy, F buoyancy, equals minus rho, no, we'll remove the minus buoyancy upwards. Let's just consider that. Rho G V. This is a V, by the way. The bar is just so you can differentiate it from the velocity V. So rho G V net. Let's just write it. So we know that this is talking about the whole sphere. So then if mg is bigger than rho GV, then the ball would float. But what is rho V? The density times the volume would be the mass. So a mass of the very same sphere composed of water. So in other words, if this sphere is lighter than the same sphere composed of water, the whole thing would have a higher buoyancy than the gravity, and therefore it will float. Yes? All easy. So now you have a ship. Ship tends to look like that in the front, not at the back. In the back there's a parallel area, but you will learn about that later, and we will not consider that. And by the way, we call this the free surface. It's a nice terminology to know about when considering these fluid. That's water, that's air, and that little area is the submerged area that gives us the upwards buoyancy. And this displacement, in other words, the displacement volume, and for ships we specifically call this that. Kind of looks nice, triangle. Is what gives the rho G, what gives the total buoyancy for the ship. And to ensure that the ship is floating, you have to keep this displacement volume enough. So you have to have enough of a displacement volume. If you have too little displacement volume, unfortunately your ship might sink. And that happened to many ships, including, I think, Titanic, Bismarck, HMS Hood, and many other unfortunate ship that is now in the bottom of the ocean. And that was the video for today. Thank you for watching. Oh yeah, and by the way, just a nice kind of fun fact. So there are two types of ships. Wait, let me make this more clear. So these are the two normal hull shapes. You call this the V shape, you call this the U shape. An interesting feature behind this is that for this V shape, as it sinks more, the displacement gets bigger, so it's kind of stable. For this, the displacement doesn't increase as much, so it's not as stable as V. And that's just one application of this very simple principle. And thank you for watching.